it'd be interesting to let them go together side by side and see what happens. Now, they may start off in sync, but they quickly get out of sync. And we can see that one of them is clearly oscillating with a higher frequency than the other. It's oscillating more rapidly than the other. And so they'll go wildly out of sync, and they'll come back into sync for just an instant, but then they'll go out of sync again. I think it's clear that this guy is oscillating a little bit more rapidly than his friend next to him. But what properties of the system are causing this? So, two of the things that I had played with here were the length of the spring and also the mass that's on it. Now, you can't do a true scientific experiment when you're varying more than one property at the same time here, because we need to isolate the variables of interest. And that may require separate investigations. For one of them, we could focus on perhaps just the mass that's on the spring and see if we vary the mass of the system while keeping the spring length the same, will that play a part in the frequency and period of these systems? So in another investigation, we might vary the length of the spring, but keep the masses on them the same. We want to have just one independent variable at a time, and then we can see how the frequency and period respond to the changes that we make in that one variable. So what I mean is, instead of using the heavy mass here, I'm going to use the same mass that's on the larger spring. And now I can test these guys together. Because I'm keeping the mass constant, the only variable here that I'm changing is the spring length. What I'd like you to do is make a prediction. So do you think that spring length will influence the period and frequency of these masses oscillating? Or do you think that perhaps it won't play a part when it comes to their frequencies? Make a prediction. If we shorten the spring length, will that create a higher frequency or a lower frequency? Or will the frequency for these oscillators remain the same? Okay, so we've got setup 1 and setup 2. Let's pull them down by the same displacement because we want to keep everything the same except for the one variable that we're changing, which is the spring length. So I, as the experimenter, am deciding to set the spring length different for these two setups. But I want to keep everything else the same. The mass is the same. Also, I'm going to pull them down by the same amount. So let's pull each one down by 10 centimeters. So this guy is hanging at the 47 or so, 48 above ground. So let's pull him down then to the 38. And this guy is hanging at the 75 right now, so I'm going to pull him down to 65. So both of them now have a 10 centimeter displacement. Let's see what happens. Okay. Clearly their oscillations were not in sync because they didn't go down and up together. They were out of sync. So one of them must have been oscillating faster than the other. Let's try it again. It may be tough to tell just by eye. So we have a method of figuring out what the frequencies of these oscillators are. All we have to do is time them, see what the period is, and then we can turn that into a frequency. You might decide to just do one oscillation and get the period that way. So I'm going to do one oscillation and I get 1.08. I think I'm a little slow in clicking it when I release. I think that's the problem. I don't think I'm really clicking right when I release it. So to correct for human error, I might do 10 oscillations and time that instead. All right, so ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so that gave me 11.67. If I divide that by 10, then that's going to be 1.17. So at the beginning of this activity, we had measured the equilibrium length of spring 1, and it was 73 centimeters. That's the stretched distance from the rod to the top of the mass. It was 73 centimeters for spring 1. So let's put that here. And when it came to the period of the thing, I just determined that it was 1.17 seconds. And so the frequency comes out to 0.85 cycles per second. And so now what we're going to need is we're going to need the length of our shorter spring as well. So let's get the length of it when it's in its equilibrium position. It's 10, 20, 30, 43. 43 centimeters. And we're going to have to time it. So let's pull him down by 10 centimeters. I'm going to pull him down to this position. That's 10 centimeters below where he started. And let's do 10 oscillations again. Start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I got 8.95 seconds for 10 oscillations. If we divide that, we're going to divide that by 10. That's going to be 0.895 seconds. So that's our estimate of the period. So I get 1.12 cycles per second. And so what we see is that the shorter spring length resulted in a higher frequency of oscillation. So another thing we'd like to investigate is, does the size of the mass that's hanging from the spring affect the frequency of the oscillation? So what we can do is we'll this time use the same spring. So instead of using this one, we'll just use this spring both times. One time we'll hang the small mass from it, and then another time we can hang the larger mass from it. And we'll see how the frequency responds. So make a prediction for yourself. Do you think the size of the mass will influence the frequency and period of the oscillator? Do you think the frequency of oscillation will go up when I hang the larger mass from that same spring? Do you think the frequency would go down? Or do you think the frequency will just stay the same no matter what? Make a prediction for yourself, and then we'll try it. Okay, so from our recent trial, we actually know what the frequency of this guy is already. For the short spring, it had a frequency of 1.12 cycles per second. That was with 2.5 pounds or 1.1 kilograms attached. So let's just write that one down. It's 1.1 kilograms, which is equal to 1,100 grams. We determined earlier that the frequency was 1.12 cycles per second. And let's now just check that again. Gonna pull the mass down by 10 centimeters. And let's time 10 oscillations, starting now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I get 8.95 seconds. Okay, so 8.95 was my time for 10 oscillations. And if we just divide that by 10, then this is going to be our period of 0.895. And then in order to get the frequency, we'll do 1 divided by 0.895. And yeah, it's about 1.12 cycles per second. Pretty much the same as we had found earlier. So now let's change the mass that's hanging from the spring. I'm gonna put the larger mass on. Okay, so our bottom of our spring is hovering just a little above 50 centimeters off ground. 51 centimeters or so. So I'm going to pull it down then to about there. So that's now 41 centimeters off ground. Okay, I'm ready to time it for 10 oscillations. Do you think it will be a shorter period, meaning it completes its cycle faster than the previous setup? Or do you think it'll be a longer period, meaning it takes more time to complete a cycle? Or do you think the period will just remain the same no matter what the mass is? Let's find out right now. Ready and start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I got 12.82 seconds that time. This is for a 2.3 kilogram mass, which is 2,300 grams. Our period is going to be 1/10 of 12.82. So period is 12.82 seconds divided by 10, 1.28 seconds. Then our frequency is going to be 1 over that. I get 0.78 cycles per second. All right, so the conclusion I believe here should be that increasing the mass that's hanging from the spring results in a lower frequency. Of oscillation. So there are other variables that we could investigate as well besides spring length and hanging mass. We could investigate a thing called the stiffness of the spring. So springs have a property called stiffness, and so the spring that I have selected here is fairly flexible. It's a little bit stiff, but not too stiff. But here's an example of a very stiff spring. Okay, I got this spring at a hardware store, and it is, really tough to separate, really tough to stretch it. So this is a very stiff spring. What we might do is compare the spring of low stiffness to a spring of very high stiffness. So if I was to hook up the large mass to both of these springs, well, what do you expect would happen? Do you think the stiffer spring would cause a higher frequency, or a lower frequency, or the same frequency perhaps? So we already tried the big mass with this spring. Let's see if I can hook up a stiff spring. So I think I'll hook them both up at the same time. Now we just did this one, and we found when we're talking about the heavy mass and the short spring, we had a 0.78 cycle per second frequency. So now let's hook up a 2.3 kilogram mass to the stiff spring. Okay, so it is attached. And don't be fooled by how thin the spring is. If you do look closely at this type of spring, we can see that it's finely coiled. Yeah, so a lot of strands per centimeter. All right, so I'll attempt to displace this guy by 10 centimeters. Interestingly, with this setup, I could do them both at the same time. So make a prediction for yourself. I'm going to try to pull each of them down by about the same amount. I'm going to go with probably like 5 centimeters. And let's see what happens. Do you think one of these will oscillate more frequently than the other? Let's see. Ready? And go. So they don't appear to be in sync. They get into sync, but then they go out pretty quickly. And it looks like one of them is oscillating more rapidly than the other. All right, so to calculate it mathematically, what their frequencies are, let's use the timer. So I'm gonna get the time for 10 oscillations of this setup. Pull them down. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So only 8.42 seconds. This guy took 12 seconds, as I recall. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12.75 seconds for the spring that's not as stiff. Let's check this guy again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8.57 seconds. Now you could argue that the difference between them is having to do with the length, let's say, of the springs. Now doing this at home, I didn't have access to springs that were the same length and different stiffnesses. I do have those at one of the labs, but I don't have them here with me now, unfortunately. When you do compare the lengths, they're a little bit different, so that's something to consider. Okay, so for this one, I'm gonna have to do this at the lab in a future video, perhaps. So what I call the flexible spring, that's gonna be this one here. It had a frequency of 0.78 cycles per second. And then we have the stiff spring. And that was this one here. The time was 0.85 seconds for one oscillation. 1.18 cycles per second. And so the stiffness of a spring is measured in what's called newtons per meter. You have to know how much force the spring is exerting per meter of displacement. So that is something that I can actually calculate here. The spring constant of each of these is going to be called K. And K has a formula of force divided by displacement. So if I take a look at the mass that's on the spring, this is a 2.3 kilogram mass. We can calculate the force that mass is exerting on the spring. To do it, we would use a formula for weight of an object. Okay, so this is the weight or force of gravity acting on the object will be its mass times the acceleration due to gravity, where G is 9.8 newtons per kilogram near Earth's surface. So what I'm going to do is I'm going to replace the force with mg. and we'll get mg over x. This is going to be a formula here for the stiffness of the spring. So let's multiply the mass that's hanging from the flexible spring times 9.8 newtons per kilogram. So this is mass times the acceleration due to gravity, and then divide by displacement of the free end of the spring. Okay, so if I was to remove the mass, the spring would hang out there. So just about right at the top of the post, okay, when the spring is not being stressed. Okay, but now let's put the mass on. See how far down it goes from there. So that's 10 centimeters, 20 centimeters, 30 centimeters, about maybe 39 centimeters of displacement. So we need to turn that into meters. So that's 0.39 meters. Therefore, if I calculate that, I estimate the spring constant of the flexible spring to be about 58 newtons per meter. And now let's just do the same calculation for what I call the stiff spring. And so this is going to be K equals, 2.3 kilograms, the same mass and the same gravitational field strength. And now let's check the displacement of the stiff spring. Now, what makes it the stiff spring is that its displacement when stressed like this is not going to be as much as the displacement here. So here we saw 40 centimeters of stretch when you put a 2.3 kilogram mass on it. Here I've got a 2.3 kilogram mass on the stiff spring, but we don't see as much displacement. In fact, there's not much at all. But it is something we can estimate. So let's see. When I take the pressure off here, we see that the end of this spring is just about lined up with this mark here. That's the 10, 20, 30, 40, 50, 60. That's the 70 centimeter above ground mark. And when I let it hang freely, it's down as low as maybe 66. So I think there's only about 4 centimeters of displacement here, which means there's a lot of force being exerted when this spring is stretched by even just 4 centimeters. You can tell, when I try to stretch these things, I don't have too much trouble with this one. But with this one, it's really tough. So let's try the calculation then with 4 centimeters. That's 0.04 meters. And so let's see what that gives us. So I get 560 or so newtons per meter. So that is about 10 times the stiffness of the other spring. And so we could write those in. 58 versus 560. So in physics, there is a formula for determining the period or frequency of a simple harmonic oscillator. The formulas are these. The period of the simple harmonic oscillating mass on a spring will be T equals 2 pi times the square root of m over k. So m stands for the hanging mass, and k stands for the spring constant. So I do want to point out that with this stiff spring, his displacement is actually probably being underestimated here, because the spring really does want to coil up tighter than what its mass will even allow. What I mean is that this spring would contract more if its mass wasn't getting in the way. It's one of these springs where it snaps to like a minimum length where the tension in it wants to contract more, but because the coils are touching, it's not allowing itself to do that. So I suspect if it didn't have that problem, that the spring would be shorter, and the displacement that occurs when you hang the mass should be longer if we really are to compare it to this situation. I just see that theoretically, if we are to calculate the period for the flexible spring, it matches up quite well with experimentation. We'll do 2 pi times the square root of 2.3 kilograms divided by the spring constant I determined, which was 58 newtons per meter. If we calculate that, we get something that matches up really close. The formula predicts a period of 1.25 seconds for the flexible spring. And this is theoretically. And our actual period was 1.28 seconds for this trial. So here the theory matches up really well with what we found in experimentation. And yeah, so the formula for frequency, that's going to be 1 over the period, which is going to be 1 over 2 pi times the square root of k over m. And let's see what that would be for the flexible spring. 1 over 1.25, or if we do the whole formula, .80 cycles per second. The experimental was 0.78 cycles per second. However, if we now do the calculations for the stiff spring, the formula breaks down a little bit, I think, because of the nature of that spring. And it has certain behaviors that the other spring didn't have that are unusual. So plug in the 560 newtons per meter, which, like I said, is probably a bit of an overestimate. We get that the period theoretically should be 0.40. And that is quite a bit below what we had found in reality. The reality was the stiff spring had a 0.85 second period, not 0.40. So one way we can try to recalculate the spring constant of the stiff spring is this. Instead of letting the thing just contract to a point where it is completely having all of its strands touch each other, so this distance here, I let that be the displacement x. And I was basically saying that we're hanging no mass from it when it's in this position, and the x ended up being 0.04 meters. And then I said that we were now hanging 2.3 kilograms from the mass. And so I used the formula that K would be the force divided by the displacement. And so I used 2.3 kilograms times the 9.8 newtons per kilogram. And then I divided by 0.04. This is what gave me around 560 newtons per meter. However, I'd like to now try it in a little bit different way. What I'm going to do is I'm going to recalculate, and the way I'm going to do it is I'm going to hang two different masses from the same spring. I'm going to hang the 1.1 kilogram from it first and see what that position is. Then I'll hang the 2.3 kilogram mass from it. And what I'm wanting to get here is the difference between those two positions. I'm going to let that be my x. And then when it comes to the force here, I'm going to do a subtraction. That the change in force here is going to be gravitational constant times the change in mass. All right, so what's the change in force going to be then? It's going to be this 9.8 newtons per kilogram times the difference between the 2.3 and the 1.1. So there's a change in force being applied to the spring. We're going to divide by x here to now get the spring constant perhaps a little more accurately. Okay, so see, it's not even enough. All right, so it turns out that even just hanging the 1.1 here from the thing is not enough to cause it to displace at all. So what we're going to have to do is we're going to have to get an even heavier mass than the 2.3. Okay, so back to the drawing board here. What we're going to do is we're going to use the 2.3 and a 4.6. We'll have to. All right. Okay, so there's the 2.3. Now I'll put two more of these 2.3s together. Okay. As we can see, the actual displacement between these is much more than 4 centimeters. So it's more than we originally thought. So let's see about how much it is. So this spring comes in right at about maybe 65 or 66 centimeters. So that's 60, 50, and then here's the edge of the spring with the heavy mass on it. Comes in at about 46 or so. So I think the actual displacement is more like 20 centimeters rather than just 4. So let the x difference between the two be 66 minus 46 equals 20 centimeters. Yeah, but we have to change the 20 centimeters to meters. And the spring constant may be only 113 newtons per meter instead of what I had originally calculated of 560. So really 560 was not realistic. It's a severe overestimate of the K for the stiff spring. So let's do the calculation again using 113 newtons per meter as the stiff spring's constant. So I'll get rid of the 560 and put 113 in its place. And now we get 0.89 or 0.90 for the period. And that matches up quite a lot better. We had found 0.85 as the true period in reality. All right, so yeah, just fixing our approach there. It let us explain why the problem had occurred, and we were able to fix it. And let's see if we can compare the frequency. Let's see, for the stiff spring, it's going to be 1 over 2 pi square roots of 113 over 2.3. And it says the frequency should be 1.12 cycles per second for the stiff spring. That matches up pretty well. We had 1.18 experimentally. So I think we can conclude that stiffer springs result in a higher frequency of oscillation. Another thing we should test here is, does the initial displacement of the spring, in other words, does the amplitude of the spring's motion affect the frequency of the motion? So what we'd like to see in this experiment is, does it make a difference if we pull the spring down by 10 centimeters versus, let's say, 20 centimeters? Okay, would that perhaps change the frequency of oscillation? So we can test that real quick. So first, let's pull it down 10 centimeters and start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I got a time of 12.4, so that really means that the period is 1.24. And the frequency then will be 1 over 1.24, 0.81. And now let's try 20 centimeters and see if there's any change. Okay, so it was here. I'm gonna try to pull it down. Okay, so I got it at 20 and start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, that time I got 12.48 seconds, and that's pretty much what I had before. So 1 over 1.25 gives us a frequency of 0.8. So there was no change. Now we could also try a very low amplitude. Okay, so maybe I'll just pull it down just 1 or 2 centimeters. I'll just pull it down 1 or 2 centimeters and start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I get 12.35, so just about the same. So the period does not appear to be affected by the amplitude. And we can even see in the theoretical formula for a period, the amplitude or the displacement here isn't really part of it, because it's not believed to affect the period or the frequency. One last thing we could investigate is, does the duration of motion affect the frequency as time goes on? In other words, is the frequency of motion roughly the same at the 10th oscillation as it is at the 80th oscillation? Well, one way to check that would be to first set the thing in motion and check its frequency right away, which we did already. Then what we do is another trial where we set it into motion, and this time just wait and check its frequency much later on, like say 30 seconds after it's been bouncing. And then we could do another trial where we set it in motion and wait 60 seconds and into the motion to see if there's any change in the frequency over time. So what I'll do is I'll set my timer. Okay, I'm gonna set the timer for 30 seconds for the first trial. Let's pull it down by 10 centimeters. So from here down to here, okay. And I'll start the clock. I'm just gonna wait for 30 seconds. And when the 30 seconds is up, I'll use my approach for measuring the frequency at that time. Okay, that's 30 seconds, so I'm gonna start calculating now. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so for that I got 12.43. That is a similar period that I had before. This time let's wait 60 seconds. Okay, so I'll set it into motion now. And we'll have to wait 60 seconds and then we'll check it again. If you notice, especially with this particular spring, you may notice as time goes on that the amplitude looks like it may be decaying. So I give it a certain amount of energy when I hold it down and release it. And as we see, as time goes on, it doesn't seem to be bouncing quite as vigorously as it was at the start. And that's because there could be losses of energy to the environment. Things like friction, air resistance. All right, there's 60 seconds. So let's do the calculation of the frequency. So start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so it's 12.58, very similar to what we had before. I don't believe it's substantially different. .79 cycles per second. Let's try 90 seconds here just to be sure. Okay, let's give it 90 seconds. Start. Okay, 30 seconds has gone by. Seems like the amplitude is decreasing a little bit. But what we're seeing is, even though the amplitude may be decreasing as time goes on, it looks like the frequency is not. Frequency is remaining constant because it's really a property of the mass and the spring constant. Look how much smaller the amplitude is now. Okay, there's 90 seconds. Let's time it. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there we go, 12.32 seconds. I think the differences here are negligible. I think it's just due to natural variation, just probably my own experimental error. My timing is probably to blame. And this says that the frequency is 0.81 cycles per second.